Welcome to Sundar's lecture. This is lecture number 97, and in this lecture we are going to see three-phase power with balanced load. See, we have two types of connections. One is star connection and one is delta connection, right? So we are going to see what is the power in a balanced load if it is star connected and also if it is delta connected, right? So first in star connected load, see this one we know all these kind of basics, right? This is ZP, ZP, ZP if it is balanced load, and this is the line current we are giving here, and this is nothing but between these two lines we will give the phase current, phase voltages, right? So now if you want to write what is the active power active power in this particular circuit. So maybe active power in each phase, maybe in each phase. What is the active power? Maybe I will write it as P active power. Okay, that is P per phase will be is equal to whatever the voltage across these 2 points. That is nothing but it is VP. That is V. That is it is VP. Not this is not line voltage. I have told you this is line voltage, but this is phase voltage. It will be between neutral and a single point. It will be a phase voltage, and IP into power factor, since this is AC circuit. Obviously you will get a power factor, right? So these kind of things we have seen in a single phase AC. So this is the per phase power if the connection is star connected, if the load is star connected, right? So for example, if you want to find what is the total active power, total active power, then PT will be is equal to, maybe if you see this is PA, PB, PC. If you consider this is one phase, this is second phase, and this is third phase, then what will be the answer? It will be all these values will come again. So what you will get? You will get VP IP into power factor, and then plus this is for A phase. Maybe this is A, this is B, and not B, this is B, and this is C. For example, this is one phase, and this is for A phase. For example, this is for A phase, and if you want to find for all the phases, then you will get three times this values, right? This will be VPIP power factor. This is for A phase, this is for B phase, plus VPIP power factor, and this is for C phase. And what is the total value you will get? What is the total value you will get? Obviously, PT will be is equal to 3 into V phase, I phase into power factor, right? So now this is the formula. For the per phase power in a star connected balanced load, right? And also you see we know one thing, that is in star connection VL is equal to root 3 times V phase. We know this one. This is magnitude value, and also IL, which is also is equal to I phase, right? Both are same if it is a star connected system. So if you are going for total power, then again if you are going for total power, then what you can do, you can just replace this V phase into 3 into root 3, right? 3 into root 3, and what you will get, instead of this value you can substitute phase value, then it will be VL by root 3, right? It will be VL by root 3. So 3 into VL divided by root 3, and then these two are same, so it will be into IL into power factor, right? This is the whole idea. And if you are simplifying this, what you will get, PT, that is total power, will be is equal to root 3 VL, and this will be IL. And what is power factor? Power factor, which is cos pi, that's all. So this is the final power equation, right? This is the final power equation, and this is per phase, and this is by using the line voltages and line currents, right? So this is the power in the star connected system, right? Next one, three phase power in delta connected system. See, this is very simple. Again, this is the line voltage and this is the phase. Both are same here, and we know in delta connection, VL which is equal to V phase, and IL which is equal to root 3 times I phase. We know these two kind of things, and here also there are three phases A, B, C, and if you are going for a single phase power, then the power per phase will be is equal to again VP and then IP and power factor. Maybe I will write it as cos phi. Right, this is the value. And if you are going for total power, then it will be PA plus PB plus PC. If you add these three, then obviously what you will get as PT will be is equal to 3 times V phase, I phase, and then cos phi. This is the power, total power, right? If you are writing it with the per phase, this is the total power. And again, what will be the power if you are going for line voltages and line current? You just replace here again. So what you will get here? So PT will be is equal to 3 is there, and VP can be written as VL. IP can be written as what? IP can be written as you just bring it to down, so it will be IL divided by root 3 into cos phi, right? This is the substitution, and if you simplify further, what you will get? PT will be is equal to root 3 times VL IL cos phi, that is power factor. And you see here, simply in both cases, this is for delta connected system, and you can see here this is for star connected system. At both cases the power values are same. There is no difference in the power values, whatever it may be. The power values in star connected system and the delta connected system in three phase balanced load, it will be same. That is the point you have to note here. And you see, this is the single phase power. We have seen these kind of things already. I have derived the expression for real power, reactive power, and then we have seen what is apparent power. Please refer my AC circuits lectures. You can easily understand what is the AC power. In AC power, we will have the repetitive powers or reverse in negative direction powers, and we generally call those kind of powers as reactive powers, and we have derived the equations. Right? So P there, it will be VI cos pi, and then Q, that is reactive power, we would have derived it VI sin pi, right? VI sin pi. And this is the equation, and also if you are going for yes, it is V into I. This is apparent power, right? So these kind of things we would have already derived, right? So what we have done, this is the um, voltage curve, and this is the current curve. See here, current is lagging. Current is lagging by a phase, by an angle pi, right? That is also, so V will be is equal to, here it is Vm sine omega t, right? This is omega t, and I will be is equal to Im sine of omega t minus pi. And if you simplify this, they just substitute P is equal to V into I, and then you just substitute all these kind of things, and you will have magnitude of VI cos pi one thing, and then VI sin pi at one thing, and VI cos pi never gets to 0, and VI sin pi, it will be a repetitive power, or we can say oscillatory power, and those kind of powers we are calling it as reactive power, and non-repetitive powers, that is only positive direction powers, are called as the real power, and all those kind of things we have already seen. You just please refer my previous lectures. And if you are going for three phase power, see this is the voltage, three phase voltage. We know these kind of things already. We have seen what is VA, VB, VC, or VR, VY, and then RYB, VB, all those kind of things, right? So VA will be the reference voltage, and VB will lag by 120 degree, and then VC will lag by 240 degree from VA. All those kind of things. This is voltage, and this is current. And if you see both things, right, whatever it may be, see this is the power curve, three phase power. If you multiply these two, P V into I, you will get like this. And if you are going for the uh, final expression, the power in a three phase circuit, it will be a constant value. It will be a constant value. It will have only above zero values, only positive values you will have, and that is what we are going to derive here in this equation. See, for example, we know, right, what is VA here. So I'm just writing it as maybe I will write here, maybe, okay, fine. So VA will be is equal to VM sine of omega t, that we know. And then what is VB? VB, then it will be is equal to Vm sine of omega t minus 120 degree, minus 120 degree. And what is VC? VC will be is equal to Vm sine of omega t minus 240 degree, right? Minus 240 degree or plus 120 degree, anything it may be. And what I am taking current IA, that is equal to Im sine of omega t minus pi degree. Maybe this is degree. And IB, which is equal to Im sine of omega t minus 120 degree. It is already there, and you have to take it as minus pi. See, you have to understand, this is natural minus 120 degree, and this pi, which is nothing but I am taking it as the power factor angle, maybe the angle between voltage and the current. If it is minus pi, then what it actually means? It is an inductive load. It is an inductive load. If current lags the omega t by an angle pi, then it is an inductive load. If I put plus here, then what is that? And that will be the leading power factor. Then it will be a capacitive load. All those kind of things we have already seen. So this is IC, and IC I am just taking it to be Im sine of omega t minus 240 degree minus pi, right? So this is now the values of VA, VB, VC, IA, IB, IC, right? All those kind of things we have written here. Now, what is the P into omega t? Then what will be the power, total power? So total power, we know it is a VA into IA, right? This is VA into IA plus VB into IB plus VC into IC. Now we have to multiply all these powers, right? So I will write here P of omega t will be is equal to it will be Vm sine omega t. This is one part, and multiplication of Im sine of omega t minus pi, that is first one. Then plus it is Vm sine of omega t minus 120 degree multiplication of Im sine of omega t minus 120 degree minus pi, right? This is one part. Then plus this is Vm sine of omega t, and here also, right, omega t minus 240 degree minus pi, multiplication of, you will get Im sine of omega t minus 240 degree minus pi degree, right? Oh, sorry, here you will not get this one, right? This is only minus pi. You will not get this. I have written wrongly. So this one, right? So this is the multiplication. This is the multiplication we have to do here. See here in this equation, you see both these two terms. Here Vm, Im, you just take it outside. You just take it outside. What you will get? Sine omega t, sine of omega t minus pi. And then in these two, you see again Vm, Im. If you take it out, it is sine of omega t minus 120 degree. Here sine of omega t minus 120 minus pi. So it will be sine of AB formula, right? So what I am going to do, I'm just going to substitute sine A, sine A and then sine B formula. So if I substitute sine A, sine B, what is the formula for sine A, sine B? It is 1 by 2 into cos of A minus B, cos of A minus B minus of cos of A plus B. Just use these formulas into this expression, and you will get a final expression. I'm just writing out the final expression. What I'm getting for P of omega t, I'm just getting it to be Vm Im total multiplication of 1 by 2 cos of 1 by 2 cos pi minus cos of 2 omega t minus pi, right? 2 omega 2 minus pi in plus 1 by 2 cos 1 by 2 cos of pi minus cos of 2 into omega t minus 120 degree minus pi, right? This one, second term, and then plus again you will get 1 by 2 into cos of pi minus cos of 2 into omega t plus 120 degree minus pi. So this is the final expression you will get after substituting the sin A sin B formula. And then if you further simplify this, what you will get, P of omega t can be written as 1 by 2 Vm Im, 1 by 2 Vm Im, and then in this one it is 3 cos pi minus cos of 2 omega t minus pi, 2 omega 2 minus pi from the first one, and then from the second one it is minus cos of 2 omega t minus 240 degree minus pi, and then in the another term it will be minus cos of 2 omega t plus 240 degree minus pi, right? So this one you will get like this, right? So what we have to do here, I have made any mistake here, it is 120 degree, right? Yes, I have made a mistake. See here also I have just leave one bracket, right? So it will come like this, and this is 120 degree, not 240. It is 120, right? It is 120 degree. So now this is the equation, and if you further simplify this, so P of omega t, you will get 3 by 2 Vm Im. See, I'm not telling you what is the content I am made here. Just you simplify this. Obviously, you will get these kind of expressions. So 1 by 2 Vm and then Im, and then inside this you will get cos of 2 omega t minus pi, that is one term you will get, and then plus cos of 2 omega t minus pi minus 240 degree, and then plus you will get the cos of 2 omega t minus pi plus 240 degree. So this is the equation you will get if you further simplify this. And you see, we know the cos of 2 omega t will always give you what? 0. So this whole term, all these terms, and now maybe I have missed here one thing, that is cos pi. I have missed out, right? This is cos pi. See, this whole term will become now 0. Now it is 0. So what is the final expression of P of omega t? So P of omega t can be written as, see, it is 3 divided by 2. It is 3 divided by 2 Vm Im cos pi, right? So this is the final formula for the three phase power, instantaneous power. At any instant you take, at any instant, that is what we have drawn here. That is what we have drawn here. This is the power curve. It is a constant value. Try to understand. See, in three phase, at any instant you take, at any instant you just measure the power, you will get a constant value. Not, it is unlike in single phase AC, you will not get a only constant value. You will get another term with this, that is nothing but we will always call reactive power. But here you will obviously get only the constant power, only the constant power. See, what is the next topic we are going to see? It is complex power. See, in complex power, what we are going to write, see, for each phase, maybe P for each phase, what is the power? It is Vp, Ip, and then cos pi. This is the real power. This is the real power. And if you are going for reactive power, that is Qp, then for each phase it is Vp, Ip, and then I can write it as sin pi. Right? We know these two formulas per phase real power, and then I have written for the reactive power. Then what is complex power? And we have seen these kind of things. See, we know what is the single phase complex power, what is the single phase real reactive power, all those kind of things. That here it is same thing, but we have three different phases. That's all, right? So the complex power, this is per phase. Try to understand complex power per phase. So complex power per phase, if I am going for per phase, then SP will be is equal to P per phase plus J into Q per phase. And this is nothing but we can write it as Vp into IP star. See this star, why we are using this star? These kind of expressions also we have seen in the single phase circuits. See, you just go through my single phase circuit power so that you can easily understand what is the three phase power. And so for three phases, for three phases, real power can be written as what? Real power. So real power, that is PT, can be written as PA plus PB plus PC, and what you will get? 3 PP. 3 PP, that is nothing but 3 into V phase, I phase, cos pi, right? And similarly you can go for QT, and again you will get 3 into V phase, I phase, sin pi. And also this expression we have seen, root 3 VL IL cos pi, and this one also can be written as root 3 VL IL sin pi. See, these kind of things you can easily understand. And also, what is the complex power? Complex power ST, that is total ST. You can write it as 3 into SP, 3 into SP, and then this one can be written as 3 into VP IP star. Simply you can write this is the complex power. And also you know another formula, that is a 3 into I square P into ZP. That is also one part. And also you can write another formula, that is nothing but it is 3 into VP square divided by ZP star, and we have derived these kind of expressions. So at last, finally, what you can write, this ST, that is total complex power, can be written as PT plus J QT. right? So this is the complex power of the three-phase balanced load. See here, ZP is the per phase impedance. You have to understand. ZP, it is a per phase impedance. So this is the complex power of a AC three-phase AC balanced load or power, complex power, right? Right. We will take a numerical problem now so that you can easily understand, right? So this is the first problem to the balanced load as shown in the as shown to the balanced load as shown a balanced load three phase voltage of 208 voltage. Here it is 208, that is 208 voltage between two line is applied. Calculate the total real power and reactive power drawn by the three phase load. So they have given you what is ZP and everything. So you need to find what is the value of real power and the reactive power, right? So here they have given you the line voltage, right? So if it is a phase voltage, then what you have to do? If it is a phase voltage, then VA can be written as VA phase can be written as VA divided by ZP, right? So this is phase voltage, right? This is the phase voltage. And if you want to find what is the phase voltage, then how will you find the phase voltage? Sorry, I made a mistake. I made a mistake. This is wrong. See, what is they have given you the VA, they have given you as 208 voltage. This is line voltage, and since this is the star connected load, and if you are going for VA phase, VA phase voltage, then it will be 208 divided by root 3 at an angle of 0 degree volt, since I am just taking A to be the reference voltage. So if you want to find what is the current IA, that is phase current, that will be is equal to VA divided by ZP. So this is the IA phase. So that should be is equal to what is VA phase? It is a 208, that is 120 degree. You will get it as 120 degree. So if you simplify this, you will get this as 120 degree. So it is 120 degree divided by, and here they have given you 4 plus J3, right? That is ZP. If you convert this into polar form, then you will get 5 at an angle of 36.9 degree. And if you simplify this, you will get 24 at an angle of minus 36.9 degree amperes. Now you see what is the ST value. It is very simple though. ST can be written as 3 into VA and IA star, right? That is what we have seen here. That is what we have derived here. So if you further simplify this, what you will get? It is 3 into 120. You have to go for amplitude value. 120 into, it is 24, right? It is 24 at an angle of minus 36.16, means it is plus 36.9 degree, right? So finally ST can be written as 6910 plus J5180 volt ampere. See, you just try to convert this into rectangular form. And what is this value? This is nothing but PT. And what is this value? This is nothing but QT, right? So PT, it is 6910 watts, and what is QT? It is 5180 VAR. Try to understand, right? So this is the complex power of this particular balanced star connected load, right? So we have seen an example, right? You just take a delta connected load and you simplify that, you will get the answers like this. Thank you. We will see in the next class.